this is Junichiro Horikawa, and this is the 10th episode for VEX for algorithmic design. And the topic today is the basics of volume using with VEX. In these sessions, I'm going to show you the basic way how you can modify the volume using VEX, together with some exercises so that you can be familiar with how you can deal with volumes. Today I'm just going to show you the basics, and later on in other video I'm going to show you more advanced way how you can deal with volumes with VEX. Now before getting into the detail, let me explain what volume is compared with a mesh geometry. Now, until the previous sessions we were dealing with a mesh geometry, which has a face information plus a vertex informations, so that you can use point wrangle to deal with the points or vertices, or primitive wrangle to deal with a primitive, in this case a face. When it comes to volume, it is totally a different type of geometry type compared with mesh. You can consider volume as a 3D grid, which in each grid cells you have a different type of values, and each cells in a volume is called as voxel. And you can store numerical values in each voxels, such as 0.5 and so on. And the type of the value which you can store inside a voxel could be either a float value or a vector value. The numerical value, the float value, is mostly used for visualizing like fog-like environment. Including smokes, fires, and so on. Vector values in voxels can be used to display a color, like RGB, using RGB for X, Y, and Z, or can also be used for the vector field to control the movement of the geometries. And since the volume is a 3D grid, you always have this boundary together with the size for the X, Y, and Z. How many voxels you have in X direction or Y direction or Z direction. Meaning if you have small number of X, Y, and Z, then you'll be having a low res volume. Now it might sound a bit weird after doing several steps dealing with mesh geometries, but dealing with volumes is also a essential things when it comes to do algorithmic designs using mathematical operations to do some geometrical modifications. So we need to have some basic understanding how volume works and how we can modify volumes. If you know how you can deal with volumes, you can do a lot of complex geometrical operations, which will going to be really interesting and cool. Now in Houdin, there is mainly two types of volumes. One is called a fog type and one is the SDF type. And the one that we're going to deal with is fog type in these sessions. For the SDF type, I'm going to talk about it in other videos. It's going to be a bit more advanced topic. The fog type volume is the one that I was explaining about. It is a 3D grid with a voxels, and each voxels you have a density value in order to express like a fog-like environment. Now SDF is also a 3D grid volume, but the evaluation for each voxels is a bit different compared to the fog type. It is mostly used to visualize the surface. So what it does is to extract the surface in between the voxels, which has in between the positive values and the negative values. So it's mostly used for the modeling and not for simulations purposes like fluid simulations and so on. Fluid simulations can be used with the fog. For SDF, you want to use it for more like a surface modeling with the detail. But in these sessions, we're not going to go into detail for the SDF, maybe on later videos. Now let's first see how we can create volume and how we can modify a volume values, both a flow values and vector values. So let's start by creating a geometry node, and let's try to create a volume. Now there's mainly two ways to create a volume. One is to convert a mesh geometry into a volume, or one to start from scratch. In order to create the volume from scratch, you can use the volume node and this will create a box shaped volume, which you can use these parameters like uniform sampling divs to control the resolutions of the volume. And if you show up the informations of this node, you'll be able to see this item right here saying 50, 50, 50. So this is the information about the volumes, and it says the voxels is 125,000 voxel, size 0.02. So those are the informations of this voxel that I have just created. And if you go to the geometry spreadsheet, you'll be able to see one geometry per data type for point, for vertex, and primitive. These are all related to the voxels. So you can access to the voxels either from points, primitive, or vertices. But these are all considered as volume. By changing the parameter like uniform sampling divs, you'll be able to change the resolutions like this. How many pixels, how many voxels you have on X, Y, and Z directions. Now in order to change the type of values you want to store in each voxels, you can go to this parameter called rank to change what kind of values you want. Now I have told you that you can store either float values or vector values, but you can actually store matrix values as well. But in this case, we're just going to deal with the scalar and vector, which is mostly used. Okay, so we're gonna go by choosing the scalar first, and we can also set the initial values for each voxels with this parameter. The first parameter will be used for the scalar, and the second and third can be used together with the vector data type. Okay, so for now we're gonna type 1 for initial values by selecting scalar. And as you can see, by setting the initial value 1 for the first value, you'll be able to see the volume visualized as a box inside a display. Now important things to do next is to name the volume. By going into the parameter called name for the volume sections, you can set the name of the volumes that we have just created. And most of the time when you are using scalar, using density is a popular name. By setting the name, if you go to the information again, you'll be able to see the name density next to the resolution of the volumes. Having name for the volume is very important when it comes to access to the volume from VEX. So please remember to name the volume whenever you create it. Now before modifying the volume value using VEX, let's try to visualize this fog in a different ways so that we can see the changes. Now if we change the initial value for the density of the fog volume, like change it into 0.5, the volume becomes lighter or maybe even darker, and at some point it just disappears somewhere around 0.2. Now when it comes to debug the volumes, or in order to visualize the volumes, sometimes you want to show the volumes even if the value is equal to 0 to see the differences. So to do that, what you can do is to use a node called volume visualization. Okay, and in order to show up the value even if the volume density is equal to 0, you can first move this point for the density ramp to 1 to create a horizontal lines on top. Okay, and then you can change this ramp in order to change the color of the volumes based on the density values. Now to do that, you first need to set the attribute for the density, which density name you want to use in order to change the color. Now in this case, we only have density volumes, so we choose this one. Then we can try to change the color for when the value is equal to 0, when the density is equal to 0, 2, when the density is equal to 1. And let's also create a middle between values like in yellow. This. Okay, now currently it is shown as red, which means it's the initial density value is equal to 0. If I change this to 1, then it becomes blue. If I change this to 0.5, it becomes yellow, which is corresponding to this ramp parameter. So when the density is equal to 0, we're seeing this red color. If the volume is 0.5, then we're seeing yellow, and if it's 1, we're seeing blue. Now that we have visualized the volumes with the colors, let's try to modify the volume with VEX and see if we can change those values using through a VEX code. Now in order to control the density values, until last sessions we were using either point, primitive, vertex, or detail angle, but in this case, when we are going to deal with the volumes, we're going to use the special type wrangle called volume wrangle, which works on specifically on volumes. And I've just changed the name to density 1 for the volume wrangle, and see that the UI is a bit different compared to the point wrangle or primitive wrangle. You don't have an option to choose the type of geometry you want to use for, but since this is a volume wrangle, there's only one type that you can deal with, which is the density. Okay, and the easiest way, the most basic way to modify the density for this volume that I've just created is to first choose the type of the volume, type of the value stored in the volume which you want to control. And in this case, we were creating a scalar type, which is the float type values. So we can access that by saying f at as a float attribute. And you can access to the density value by using the name that you have specified, in this case density, right here. Okay, so this is the basic way how you can access to the density value that you have stored in each voxels, and simultaneously this code runs on every voxels on a volume. And let's say if I say I want to modify the density into 1, then I'll be able to get the visualized color blue. And if I say I want to modify it to 0.5, now I can change this to yellow, just like we did right here. Now since we're in the VEX code, we can actually use all sorts of VEX functions like chf to create a parameter channel. Let's create a float channel named as D and promote this as a slider by clicking this button. You'll be able to have a slider, the volume between 0 to 1. Then by changing this, you can see that the volume value is changing, and also the color is also changing. Now currently I'm changing the whole voxels with the same values so that I am seeing the same color for all the voxels. Now let's try to change the colors. Let's try to change the density for each of the voxels with different values. Something like using a noise functions, part of a random functions. Okay, so I'm going to create another volume wrangle. Connect with the volume. And I'm gonna say, name this density 2. And in this case, let's say f at density is equal to noise at p. Now by using at p, you can access to the each point of the voxels, then multiply with some values like 2. You can see that the volume has changed a bit. The density of at each position has changed a bit. Some part looks lighter, some part looks darker, and so on. But it's a bit hard to see the differences, so we can also use this volume visualization to color the volume to see the density differences. Now when we use the noise functions, the range that we can get is around 0.3 to 0.7. So let's raise up the minimum and maximum range for the density, and we'll be able to see some more clear differences between the higher density value and the lower density value, creating this kind of gradational fog environment. Now this itself is already interesting, but you can also convert the volume values into a surface as well, based on a value of the density. To do that, we can use a node like convert, connect it with the volume, and we can change it from volume type to a polygon, and then we can change this volume offset sliders, which will act as a threshold values to visualize the volume as a surface. So what it does is extracting the isosurface of the volume into a surface. So if I set the volume offset to 0.53, then that means that the surface that is close to this value has been extracted from this density map, which is also used a lot in a complex modeling when it comes to algorithmic designs. We're not going to get into detail with this isosurface thing yet, since this session is going to be the basics of volumes, but just remember that you can do something like this. Now we have just dealt with the volume with the float value, a scalar value. The next thing I would like to try out is to modify the volumes with a vector value. Now let's create a volume again using a volume node. Let's set to vector this time. And for the vector value, I'm gonna name the different names. Let's say velocity. Okay, and let's also initialize the values by 1 for x value and leave the y and z value to 0. And also set the volume uniform sampling divs to 50 to have enough resolutions. Having 50 means you have 50 voxels in x direction, y direction, and z direction. Okay, let's check this out by going into the information, and this time you see that you have 3 different volumes. One for the x, one for the y, and one for the z. So you can actually say that you have 3 different scalar volumes as well, and packed as one vector volume. Okay, and if you look at the number of points, primitives, and vertices, you'll have 3 volumes. So each volume acts as a density volume, scalar volumes, which can be used similar to the one that we have just tried right here. But you can have extra ways to access to the velocity volumes by setting it to a vector. Now let's try to visualize this vector volume first by using a volume visualizations. So first, let's create a volume visualization. And same for the density, I'm going to change the density ramp so that every value will be equal to 1. Okay, and I'm going to leave this diffuse ramp color from black to white, and I'm going to change the diffuse field right here to either velocity dot asterisk or velocity x, velocity y, velocity z. So you can choose which volume type to change the color with. Now if you choose this one, then all the x, y, and z value will be influenced by this diffuse ramp. If you just choose one of it, then only the one scalar value will be evaluated with this diffuse ramp. Now in this case, I'm going to choose this velocity dot asterisk, and as a result, the volume has become red. That is because volume x has only been activated, volume x has been evaluated as 1, meaning white in this case, and all the other y and z value has been evaluated as 0, which in result goes to a black value. So having a white value for the red color and the green and blue become 0, which will create this whole red color. And we can see the changes by trying to have a different kind of initial values. Like if I change to 0, 1, 0, you'll be able to get a green value. If I go to 0, 0, 1, you get blue values. If you have red for the 1 and blue for the 1, we'll be able to get purple-like pattern, purple-like color for the volume. So that's kind of one of the benefits using vector values. You can use x, y, and z values to specify the color for each voxels based on its x, y, z value. Okay, now let's try to modify this velocity value using volume wrangle like we did for the scalar value. Okay, in this case I'm going to name this as velocity, and since we are dealing with the vector value, last time when we were dealing with a scalar value we were using f at, but in this case we were accessing to a vector value, so what we're going to use is called v at, since this is expression for accessing to the vector attribute. And the name of the density or name of the volume that I have created is called velocity, so I'm going to type velocity to this. Now you can use set functions to set either x, y, and z value to change the velocity values, and as a result you'll be able to change the velocity like this. If I change this to 0, you can change this color. Now maybe you can parameterize all x, y, and z value for the vector and see the changes by having 3 sliders. Okay, let's copy this and name this y and z. Promote this as a sliders, and starting from 0, 0, 0, which makes the black volumes. So currently there is a volume right here, which is a bit hard to see because the background is black. If I change the background to light color, you'll be able to see the black color right here. Now if I raise up the x, the volume becomes red. If I raise up the y, it becomes yellow and becomes white if all the values become 1. So you can see that the vector volume value is actually changing with this slider value, and based on the vector volumes values, the color is changing using the volume visualization node. Okay, let me bring the background to dark again. Now I have just shown you how to visualize the vector volumes with the colors, but there's also another way to visualize the vector volume. If you think about the vector as a directional value, we can actually extract the direction from the vector volumes. So let's try to visualize the directions using a different approach. One thing I could think of is to use a volume visualization node called as volume trail. Using this volume trail, we'll be able to visualize the volume with a trail, how the volume moves with the directional vector value by supplying some points, the source points to start the trail from. Okay, so in order to create the points, I'm going to use the scatter node to create the points inside the volume like this. Then connect the scatter points, the collection of points, to the first input of this volume trail. And for the second input for the volume trail, I'm going to connect the volume with the vector value. Now we have just visualized the direction, the vector volume as direction using this volume trail. And if we change these slider values, you'll be able to see the changes with this direction, how the direction changes based on those slider values. So if only the x value is equal to 1, then we are seeing the x directional lines. We have x and y value having 1, then we have diagonal lines right here, and so on. So this is also useful in order to, if you want to use the vector volumes as a directional value instead of the color value. You might want to use this volume trail in order to see what happens inside the volume. Now I have told you that there is other way to create a volume other than creating a volume from scratch using volume node. That is to create a volume from a geometrical shape. Let's say we have a geometry like sphere, and let's set it to polygon with some high frequency. Now there is a way to convert this closed mesh geometry into a volume, and that is by using a component or node called iso offset. By using iso offset, you'll be able to create a volume that is inside the closed surface that I've provided. And you can, same for the volume that I have used here, you can set the resolutions of the volume by changing the sliders, and you can also set the name of the volume. Say if you want to create a scalar value, say density. In this case, the one that you can create using this iso offset is only a scalar value. There's no options to change the value type right here, so keep in mind. But you can actually create this trimmed out volume from a input geometry. But actually this is still a box typed volume. You have 50 by 50 by 50 volumes, 50 by 50 by 50 voxels. The only difference with the initial volume node is that the initial value has been trimmed with a different density based on the geometrical shapes. So the voxel which is inside the sphere is stored as 1, and the voxels outside the sphere the density is stored as 0. So that's kind of only the difference between using the node from scratch and the node using created iso offset. But it's pretty handy to create a volumes out of a geometry, so I think you're going to use this a lot. So as I told you, the volume right now outside the sphere is 0, and the density inside the sphere is equal to 1. So actually we can do some simple mathematical operations to a volume using volume wrangle to create some interesting shapes. So let's try to do that by using volume wrangle, and let's say mathematical of OP. Okay, and this time what we want to do is to first retrieve the density values from a density attribute by accessing to a float attribute called density. Remember to name the volume as density using isOffset. Now what we want to do next is to do the multiplications to the density that I have just retrieved. So say d multiply by chf, say mult. Now promote the sliders, which is in default from 0 to 1, and re-update the density with the updated value right here. Now I think I should say multiply equal to update the d value. Now store the d value that I have updated to the density to update the density itself. And if I make the slider, I can control the brightness of the fog or the density values of the fogs just inside the sphere, because outside the sphere it's equal to 0, so if I multiply with any values it still stays as 0. Okay, so let's try to visualize this with color by going back to the previous one. Maybe I can use this one or this one. Let's copy this one and connect with this one. Okay, now if I change the sliders, I can see that because outside of if the density is equal to 0, I see a red value, because when I use this volume visualization, if the density is equal to 0, I see red. So maybe when the value is 0, in this case, I'm gonna set it to black so that I can see it as a transparent background. Or maybe I can make it transparent, probably, if I can do that. Maybe not. Okay, and let's create another color just right next to the black one with the red color. Okay, now let's try to change these values, and we will be able to get a value in between 0 to 1, which creates this kind of gradational color from red to blue. Now you can do a bit more interesting stuff, like combining this with the noise functions, like using noise with add p multiply by chf mult. In this case, you are creating the noise value just inside the sphere. Now I might want to raise up this multiple value range from say 0 to 5, and also raise up the color, something like this, to see the differences. Okay, now it becomes interesting. Marble like volume. And if I change this multiple, I can see the value affection is only occurring inside the sphere. So this kind of simple mathematical operation does interesting jobs to a volume, and understanding each of the voxels values, you'll be able to control properly how density should work. So my advice here is to always, when you use the volume, remember that volume is constructed using a voxels, a 3D grid, and at each voxels you have values, float values or vector values, which you can control it by yourself using VEX to do a mathematical operation like this. And if you multiply the zero density with any other values, the result is always 0. Okay, next thing I would like to show you is the preserve attribute only for the volumes, which can only be accessed from the volume wrangle. So let me show you that. First thing I would like to do is to create another initial volume using volume node. Then set it to scalar, name it as density, set the initial value to 1, and set the uniform sampling divs to 50. Right, so we have this kind of box-like volumes. Now I'm going to connect a volume wrangle. And let's also connect the visualization node. Maybe I can copy it from the very first one. Okay. Now I'm going to name this volume wrangle as volume attribute 1. And the first attribute that I'm going to show you is actually we have already used it, which is called as @p, which is similar to the one we can use in point wrangle or primitive wrangle. This is a position attributes, and in volume wrangle it is specifically a position for each voxels, the center of each voxels, center position of each voxels. Now we can use this position values to retrieve either x, y, or z coordinate. So let's try to visualize and change the density of each voxels based on the either x, y, or z coordinate, maybe x coordinate. So let's try to update the density at each voxels using the point x coordinate value. And as a result, we'll be able to see some gradational color values. And since the box is in between -0.5 to 0.5 to positive 0.5 for both x, y, and z values, so the minimum density value right now is -0.5. So I guess I can change, maybe the diffuse ramp is only works with the range in between 0 to 1, so maybe I might want to fit this density value inside 0 to 1 from -0.5 to positive 0.5. I guess I can just do that by adding 0.5 to this x coordinate value. And as a result, you'll be able to get this kind of a gradational values, gradational color pattern from a density. So if it's close to 1, you get a yellow, you get the blue color. If it's close to 0, the density is close to 0, then you get a red color. So as you can see, I have actually retrieved the positions x coordinate and just changed to the density, showing you as a gradational values. If I change this to @p.y, you get a y directional gradational color. If I set to z, I get gradations on z-axis, and so on. So inside, what I wanted to show you is that in volume wrangle, by accessing to @p, you can actually access to the point position at each voxels, center of the voxels. And you can use that value to modify the density values or any purposes you want. You can also use that positions to actually compare with other geometries, like calculating the distance and so on. Now let me also show you other types of preserved attribute which you can also access only using the volume wrangle. Now I'm going to use another volume wrangle, and let's name this as volume attribute 2. I'm going to I'm going to attach the same visualization node. Okay, this time what I want to show you is the attribute which you can access to a index of each voxels together with the size, how many voxels you have on x direction, how many voxels you have on y direction and z direction. Now in order to get the index, which means for x, y and z values, you can get a integer value for either x, y and z, in which index it's the voxel, the current voxel that you're looking at inside the volume wrangle is at on right now. If we have a volume which is in between, which have a resolutions of 50, 50, 50, that means we have 50 voxels in x direction, 50 voxels in y direction, 50 voxels in z direction. And each voxel has an index from 0 to, in this case, 49, and starting from a minimum somewhere around here. So first voxel, the first voxels on the corner starts the index from 0 for both x, y, and z. And by going into the x direction, the index raised up by 1 and end at 49 at some point. Same for the z direction and y direction. And you can retrieve that index value for either x, y, and z by accessing to a preserved attribute called ix or iy or iz. And this number is related to the resolutions values which you have specified right here. Currently it's 50, so the maximum value of either ix, iy, or iz is 49, and the minimum is always 0. Okay, so let's try to use that to visualize the to change the density volumes. So f at density is ix, say, multiply by 0.02, and try to show up the color, and as a result you'll be able to get a similar result which I have used by using the point positions. But instead of using the point position, I'm using a point index or a voxel index and convert it into a density value. And if I change the multiplication to 0.01, the ranges just change like this. Now in order to, if you want to make the range of this multiplication to be always in between 0 to 1, then the best practice is to divide this x value with the total, the maximum resolutions value for x direction, in this case 50. Now to do that, we need to access this number, this values right here for either x, y, and z. And it is possible that you have different numbers for x, y, and z by changing the size for x, y, and z right here, like this. So in this case, we have 50 on x, but 36 on y and 36 on z. Now, in order to access to those different x, y, and z resolution values, maybe let's change the size for x, y, and z to different values so that we can see the changes clearly. Something like this. Okay, so 1.5 for the x size, 2 for the y size, and 1 for the z size. Okay, so if you want to access to the x resolutions size, the number of voxels in x directions, you can use other voxel, other attributes, preserved attribute, which is called as I at res x, meaning as resolution x. And we can do the division between those two values. Now the problem by dividing the values between two integers is that the result always be the integers. So if you want to get the float result from the divisions, you want to convert one of the integers into float. So I'm going to convert the resolution's value into float, and as a result you'll be able to get a value in between 0 to 1, starting from the minimum voxel value to the maximum voxel value, I mean the index. And this is for the x direction. If you want to use it for the z direction, you can change it to iz, and the resolutions in this case will be res z, and you'll be able to get the gradational values from 0 to 1 for the density, and convert it in, and be visualized as color like this. If you want to do for y, just replace this z with y, and you get a similar result. And any values you have, currently you have different number of indexes or different number of resolutions for either x, y, and z. But by using a calculation like this, you can always get a value in between 0 to 1 by dividing the current index with the maximum resolutions at that specific axis. Now, these are the three main attributes. One is at P, and one is Ix, Iy, and Z, and one is res X, res Y, and res Z. Those are the preserved attribute which you can use only on volume wrangle. I mean, not for the points, but points can be used in different wrangles, but with the different purposes. But these are the preserved attribute which you can use specifically inside the volume wrangle. So remember that. These attributes, especially for Ix, Iy, and Z, and res X, res Y, and res Z, these attributes cannot be used outside volume wrangle, like in point wrangle and primitive wrangle. So remember that when you want to have an information from the volume, always use this volume attribute, volume wrangle. Now I've just told you that you can only access to this special attribute like Ix or res X from a volume wrangle, but you can actually access to all sorts of information based on a volume, like density value, velocity value, index value, resolution value, and so on, from other types of wrangle as well, like point wrangle or primitive wrangle. And in order to do that, we use a volume specific functions. So let's try to see how we can do that. If you go to the help page called as VEX functions in a Houdini help page and search for volume, you can actually check what kind of functions are there, especially for the volumes, in order to retrieve an information for the volume geometry. So we're going to try to use some of the functions listed right here to see what kind of information we can get from other types of wrangles like point wrangles or primitive wrangle. So first of all, let's create an initial density value, initial volume with the scalar type, and name as density. Set the x value to 1, initial value, and let's also set the uniform sampling diffs to 50. And I'm going to make some randomized density by using a volume wrangle first. So I'm going to use the volume wrangle, and let's say initial, I'm just going to call init, and I'm going to update the density value at each voxels using a noise function like we used before, and maybe multiply by some value like 2. Okay, I think I was having a typo. Now I have this kind of randomized voxel value, voxel densities at each voxel positions. Now let's try to visualize this first to see what it looks like. I'm going to use this one from the first example. Okay, and there I can see that there is a gradation between the voxels with some randomized density value. Okay. Now, what I want to do is to use additional geometry information like point. I'm going to add one point somewhere in the space, and which can be moved around using this arrow. And what I want to do is to sample a density value which is close to this point. So using this point as a guide positions, and from this position I want to retrieve the specific density value which is inside this box. So in this case, if the point is close to the red value, I want to retrieve that density value which creates the red color, which in this case close to 0. And if the point is close to blue, what I want to get is the value which is close to 1. Okay, so that's what I want to do, and that is called as sampling, using the position to sample the value from the volume. So how do we do that? We could first try. In this case, I'm going to try to use the functions using volume wrangle again. And in the next example, I'm going to show you with different wrangles like point wrangle. What I want to show you here is that you can also use those functions inside the volume wrangle as well. Okay, so for the volume, by using this volume wrangle, I'm going to name it as volumesample and connect the initialized volume value to the first input to the volume wrangle, and I'm going to connect this guide point to the second input of this volume sample. Now the first thing I would like to do is to retrieve the point position from the second input. So what we can do, we can first create a attribute or a variable called pos for the vector and retrieve the point position using point function from the second input. I'm typing 1, that means I'm retrieving the information from the second input. If it's 0, you're retrieving the information for the first input. And what I want to retrieve, the position, and capital P is the position attribute for the point. So I'm gonna type P. Then there's only one point, so I'm going to specify the index of the point that I want to retrieve, and the 0 is the first point. Now I have just retrieved the position from the second input of this point. Now what I want to do is to calculate the distance between each point on a voxel. I'm using volume sample right now, so I can retrieve the point position at the voxel position, the center of the position, center of the voxel position, by accessing to add P, and by calculating by using the distance functions between two vectors, I can calculate the distance between two positions like this. So if the positions is right here, the point positions is somewhere around here, then at each voxels I can calculate the distance, right? And I can use that distance to update the velocity value, the density value, using this volumes wrangle. Remember that you can only modify the volume by coding using a volume wrangle. Using point wrangle, primitive wrangle can be used to access to the volume values, but you cannot modify the volume values using those point wrangle or primitive wrangle. If you want to modify the volume, then only option by coding is to use volume wrangle. Okay, now what I want to do is to create, first retrieve the density value from a current density, or maybe what I wanted to do is to sample a density value from the specific positions, right? And to do that, there is a specific functions to do that, which is called as volumesample. If you look at the document, it says samples the volume primitives values, and you have 3 parameters. One is the input number, one is the primitive number or the name of the volumes, and the third is the vector position. Now, when running in the context of node, to read the geometry form, okay, that's the explanation of the input. Okay, so this functions returns a density value for the volume that I have specified at specific positions. So, meaning if I input the position parameter with this position, then you can actually retrieve the density value at that specific positions using this volume sample functions. So let's try to do that by using volume sample, and the volume is coming from the first input, so I type 0 for the first parameter, and the name of the volume is called density, so I type density, and the position that you want to use for the sampling is the one that I have just retrieved from the second input, so pos. Right, now I have just retrieved the d value, which is equal to a sampled diffused sample density values right here. So what I could do is to try out replacing whole density value, all the voxel density value, into this d value and see what would happen. Okay, density. Okay. Density, and let's try to visualize this with this volume visualization node. Okay, I think I'm seeing some cache here, so let me save this and reopen this. Okay, so I'm currently seeing a single density value right here, and which is sampled from the point position at this point right here, which is a bit hard to see where that is. Maybe I can make the point size bigger, maybe a bit bigger. Okay, so currently I have point position right here, and the value is close to, I guess, 0, which is because the color is equal to red. Okay, now if I change the point position, I should be able to see the change with those color. Now let's try to see if that happens. I'm going to visualize this color together with the points. Oops. And move the point to see if the density, if the color changes. Now I can see that the color changes, meaning the sample density is changing based on the position of the point that I'm moving right now. Okay, So let's try to use the sample value that I've retrieved for different purposes. Okay, so after I have retrieved the density, maybe I can do some a bit more complex equations, like maybe have a conditions if conditions with compare with the distance. So if the distance is less than a density, like multiply by 0.5, then set the density is equal to d, else I will set the density to 0 and see what happens. Okay, now I think I am having, okay, was forgetting this curly bracket. Right, now I'm seeing something different, and by moving the point, I'm actually changing the color and also the radius of the volume surrounding this point, which is because I'm using the density that I have found for the radius in order to show which volume to visualize with the color. Now I'm seeing the other colors, in this case a density equals to 0 in the red, so it's a bit hard to see the inside. So I'm going back to the color node, and if the value is equal to 0, I'm gonna set the color to black so that I can see a bit more clearly what happens inside. Okay, now let's try to move the point again. Now I can clearly see what happens if I change the values, and I can see that the radius of the sphere is changing based on the position, based on the value that I have retrieved from the volume, which is the density value. So if the density value is small, the radius is also small. If the density is big, like if it's close to blue, then the radius is also really big. So this is how the volume sample function works. You can retrieve the density at specific position, and you can use the result for many purposes, like the one that I have just shown. Now in next examples, I'm going to show you how you can retrieve the vector value using a similar function that I use for the scalar values, together with a other than a volume wrangle like point wrangle. Okay, so I'm going to start by creating a initial volumes using the volume node, and let's set it to velocity, the vector type, and I'm gonna name it as velocity and set the initial value for 1 just for the x value. Okay, and I'm going to update the velocity value at each voxels, meaning the vector values at each voxels, using volume wrangle first. As I said, you can only modify the volumes using a volume wrangle. You can only use point or primitive wrangle to access to the volume values, but when you want to modify it, you need to use volume wrangle. Okay, I'm gonna name it init again, and I'm going to access to a velocity value, which is the vector type, and let's try to update that with the noise again, and let's multiply it with some multiplication value, like I'm gonna name it as scale. Okay, and let's set the range of the scale from 0 to 5. Can see if I can see the differences. Yeah, now I see something is happening right here. Now it's a bit hard to see, so let's also visualize this. In this case, I'm going to visualize this as a trail, meaning as a direction. So I will use a volume trail in order to visualize the direction. For the second input, I will input the volume, which was created with the init. And for this first input, I want to input the point as a starting point for the trail. So I'm going to create a scatter. And for this one, I'm going to create a point from the first volume right here. Now obviously the point is a bit too big, so I'm gonna keep it at 2, 3 and connect it to the first input of the volume trail, and as a result you'll be able to get the visualization of the direction using this volume trail. Now I am seeing the cache again. I'm not sure if I can. Okay, now it's gone. Now it seems like it's going to a similar direction. All of the lines is going to the same direction, even though you have some wavy changes right here. Even if I change these values, that is because if you use noise, what you get is the range in between 0 to 1. And if you have created the vector value result, what you get is the value between 0 to 1 for all x, y, and z coordinate. So to make the direction goes everywhere other than the positive direction, what you can do is to subtract it with a vector called 0.5 for all x, y, and z, and as a result you'll be able to create a more diverse direction. Okay, now if you change the size of the noise, you can see how direction changes based on it. Now it looks good. Okay, now what I want to do is to this time retrieve the vector value or sample the vector value from the vector volumes. Instead of using volumesample, what we're going to do next is a function called volumesamplev, and this is a function specifically to use to retrieve the vector value from the vector volume. Okay, the usage of the parameter is pretty much the same, just that the name of the function is a bit different. You have v after volume sample, and as a result you'll be able to get a vector values as an output. Okay, so I want to retrieve that attribute. I want to retrieve that density value at specific position, and this time I'm going to use the point wrangle to use that function, and together with a sphere which is placed on the center of this volume, maybe a bit smaller, might make it 0.25. Let's make it also a polygon so that you can access to a point attributes. Okay, let's check with the size of the volume. Maybe I can make it a bit bigger, like 0.3. Right, so next thing I'd like to do is since each of the point creating this sphere can be accessed using point wrangle, and currently I have this point position information at each point. So what I can do is to use each of the point position to sample the vector value from the volume that I've created right here, which is visualized like this, and as a result you'll be able to retrieve the vector value, which looks like this if you visualize it. And I'm going to use that vector value to modify this geometry. Okay, so let's try to do that. So the things that I want to modify here is the point position of this primitive, I mean this sphere. So I will use point wrangle, connect it to this sphere, and in this case I want to use the volume as a guide to change the sphere. So what I can do is to connect the volume to the second input of this point wrangle, and let's name this volumesample v. Okay, and let's use the point volumesample v in order to retrieve the sampled vector values from this volume at each of the point position, which is on top of the sphere. So each of the sphere is created with these triangles with those point positions. So for each point position, I want to retrieve the correspondent volume values out of this volume geometry. Okay, so to do that, first of all, the result value will be vector, so I'm going to create a vector variable, like name it as v or something. Then use volumesample v. Now this time, the volume is coming from the second input, so I type 1 for the first parameter. And the name of the vector volume was called as velocity, so I type velocity. And for the third input, I need to specify the position, where to retrieve the density from, or where to retrieve the velocity from, and that was at P. This is the point position, which is on the top of the sphere. Now, as a result, you'll be able to get the vector values at specific point positions. Now, we can modify the point position using this v value used as a direction. Now maybe I can multiply it with some scale value to control the lengths, how much the point should move to that direction. Okay, so promote that parameter. And currently it's equal to 0, so point is not moving, but if I increase the sliders, slowly the primitive is starting to change its positions, and each of the point positions moving in different direction, and those directions are actually retrieved from this vector volume. Okay, so let's try to merge these two values together, the deformed geometry and the volume trail, to see if the volume is if the volume is really changing based on the velocity. Okay, now I can see how much the velocity affects to the volume, to the geometry, by changing the scales right here. If I change the volume scale right here inside the volume wrangle, I start to see a shape differences based on the scale of the noise value. Right? So I can clearly see that the sampled volume is clearly used for the direction for the point to modify. To make it a bit more interesting, I could add like a value like time to this value and make it real time to play to modify the geometry on real time based on the timeline. So the volume itself is changing because the noise value is changing based on the time, and based on those noise vector value, the geometry is also changing its shape, like this. Right. So that's one of the example how you can use a volume vector volumes together with a volume sample v functions inside a point wrangle or primitive wrangle. Now next, let's try to use other functions. In this time, I'm going to try to retrieve the index of a voxel, index of the volume from a position by using volumepostoindex. And also there is a function called volumeindextopos in order to convert the index value into a position. So I'm going to try to use that as well. And as a sample, I'm going to try to pixelize or voxelize the input geometry like sphere by using those functions. Okay, so first of all, let's create a sphere with a polygon. I'm gonna set the frequency to really high value, like 50, so that I have enough point. And let's also set the size to 0.4 so that the sphere should be fit inside the volume. Okay, I'm going to also create the volume, keep the size as it is, and set it to scalar. And I'm going to name it as density, set the initial value to 1. Okay, and also set the uniform sampling divs to 50. Okay, now what I want to do now is to delete the primitive faces from the sphere and just retrieve the points. So to do that, I will use a delete node and set the pattern to asterisk and check this keep points so that I can only have the points. Now what I want to do is to retrieve the index position of the volume, which is by using those points as a referencing point. As you can see, there are tons of points from this sphere, but actually the resolution is limited for the volumes, and currently it's set as 50 by 50 by 50. So some of the points, some of the index that's going to be sampled from each of the position will be at the same index positions. Like those points which is close to each other might have the same index value for the voxel. And by using that characteristic, we can create kind of a voxelizing effect. So let me show you how you can do that. So first of all, I am going to retrieve the index value using this volume as a guide based on each of the point position. So I'm going to use the point wrangle for that usage. First, connect the points to the first input of the point wrangle. I'm going to name it as volumepostoindex, and I'm going to connect the volume to the second input of the point wrangle. Now, the one that I'm going to use is called as position volumepostoindex to retrieve the index value of the volume from the position. And as a result, you'll be able to get a vector value. But this vector value is different from the vector volume value, but it is an index value, so all the values stored inside the vector is integer, which is the x, y, z index value from 0 to the maximum number of that axis, which is equal to resolution x, resolution y, and resolution 0, resolution z. Okay, remember that. So even if it's say its vector as a return value, it is not actually a velocity value, but it is a index value, which is constructed with index integer value. That's the important part you should remember. Okay, now let's create a vector variable named as index and use volume pass to index function, which to retrieve the volume from the second input, and the name of the volume was density, and the position you want to use for the sampling is at P, which is the point position. Now I have just retrieved the index value. What I want to do next is to create a vector attribute named as index and save that value that I have just retrieved into that index attribute. Okay, now let's go to the geometry spreadsheet to check the point attributes if I have those index value correctly retrieved. And I see those index both x, y, and z stored as a value, which is all an integer value, and every point is having a different index value, and some of the points is sharing the same values, like the first 10 points or so is using the same value 25.0, 25.0, 5.0. That is because, as I said, the resolution is kind of limited compared to the really high dense point from the sphere, so some of the points is sharing the same index, which is okay for now. Now, after we have retrieved the index, what I want to do next is to use that index value to retrieve the point position at this index from the volume. So next thing I'm going to use is the function called volumeindextopos. So this time I'm going to convert the index into a position, the voxel center position. Right? So let's do that. Now, looks like I'm just retrieving the same position value that I have used when using the volumepostoindex, but it's a kind of a different value that you're going to get. The one that when you have used this volumepostoindex when using the position, you were seeking for the closest index value, right? But when you use the index to pos, what you're going to get is the exact voxel position, the center of the voxel at the specific index. So the result, what you get is different in terms of the position. Okay, so remember that, and let's try to retrieve that. I'm going to create another point wrangle. Connect it with the point and connect the volume to the second input as a guide again. And this time I'm going to name this point wrangle as volumeindextopos. Convert index into a position for the voxel. Okay, now I'm going to create a variable for the position like bpos, and use the functions volumeindextopos. Now retrieving the volume value from the second input, so I'm going to type 1, and the name of the vector volume was a density. The name of the volume was density, so I'm going to use density as the name. And then the third parameter should be the voxel, which is equal to index value in vector, and I have that value stored as an attribute called vector index. So I can retrieve it by saying v at index, and as a result you'll be able to get the position. Now what I want to do next is to update the current point position to that voxel point position. And as a result, you can see that the point has been moved to the center of the voxel, which is close to the one that has found using the volumepostoindex. and the point has been arrayed, layouted like a boxelized point. Now to see the effect more clearly, we can create a box. And set the size of the box based on the resolution, meaning I can go to the volume, copy this uniform sampling divs, go back to the box, and set the uniform scale, saying 1 divided by the one that I have copied, which is in this case 50, which will create a single box right here. Now what I want to do next is to place this box onto each of the point that I have retrieved using the volumeindextopos. So connect the box to the first input, to the copy 2 points, and second with a point list. And as a result, you'll be able to get this kind of a voxelized sphere out of this original sphere put in point position. Now, there is a chance that there is a duplicated points at the same positions after moving the points. So we could reduce the number of points using diffuse right after we have moved the point to make the whole thing a bit lighter. Okay, looks good. Now we can try to see the changes by setting the different values for the uniform sampling divs for the volumes. You see a bit more. You can change the voxelized quality. If you make it too big, like 100, you start to see some holes. Currently it's fine, but maybe if I set it to like 200, you might see some holes. That is because there's not enough points from the sphere to fill out the gaps. So if you want to fill out the gaps, then you might have to increase the resolutions of the sphere as well, like say 100, which in result might be able to fill in the hole. Right. Now I'm gonna make it back to 50 and also 50 for this volume resolution. Okay, so that's how you can use this function called volumepostoindex and volumeindextopos, which is pretty useful for many purposes as well. And there are other functions which is useful as well. Try to see how you can use it for the volume. We're not gonna go into that, but basically the one that I have shown you is the most essential functions. Other ones are useful. I think you can now go to the document page to see what those could be used. Something like maybe you can use volume res to get the resolutions value from the volumes and so on. Now these were the basics of volumes, how you can use volume with VEX, how you can modify it, how you can access to the informations of the volumes. But I want to show you one more little tips for a volume together with the VEX. As you can see right now, in order to see what value is stored in each voxels, you had to use like this kind of volume visualization node, either for velocity or a density. So currently at this point, you are only able to check the value of each voxels by looking at the color or the direction of the output geometry. But if you go to the geometry spreadsheet, you cannot actually see the values stored in each voxels, because there's only a part for points, vertex, primitive, and detail. Unfortunately, there's no sections for the volumes, so numerically it's unable to see what what exact value is stored in each voxels. And sometimes it becomes a problematic. Sometimes the volume gives you an unexpected errors because you were not aware what kind of values are stored inside each voxels. So what I want to show you here is to actually how you can debug those each voxel values stored in each voxels by seeing the exact value stored in each voxels. To do that, let me first create some initial values using the volume node. Okay, so I'm going to create a volume node again. Okay, now after placing the volume node, I'm going to name this density as the name with the scalar option. And let's also set the uniform sampling diff to 50 and initial values to 1. Right, now I'm also going to apply some group to this volume for later purposes. And the group can be either primitive, point, or vertex. Either one of each is fine, because all these points, vertex, or primitive can be axis is a part of a volume. So it could be a point, a primitive. Maybe applying a volume to primitive might make sense. So let's set it to primitive. Then let's name this just volume. Okay, now let's also set some initial densities. Currently, I only have initial value as 1 for all the voxels, but let's make it random by using volume wrangle. And let's say init, then set the volume with noise function, something like this. Okay, like we did last time. Alright, now what I want to do is to currently I have just updated each of the voxels with this noise function, so the density at each position is different, but there is no way to check the exact number, exact value, what kind of value is stored in each voxels at this moment, because if you go to the geometry spreadsheet, there's no options to show the voxel values. But there is a way, actually there's a way to show that values by using a little trick right here, and that's what I want to show you right now. Now you can do that using volume wrangle. And so let's try to connect the volumes that you want to retrieve the values from. And then let's name this debug. Okay, so in order to retrieve the values, what you can do is to add a point on each of the voxel positions and set the attribute to those points using the density. So that's the little trick that you can use to show what exact value is stored for each voxels as a density. So first of all, you can retrieve the density value using f@density. Then you can create a point at the exact voxel positions by accessing to at p. So in the volume wrangle, the at p means each voxel position, and I'm using that position to add point geometry like this. By doing it, oops, I need to say add point. By doing it, you can fill out the boundary box with all those points, and each of the point position is equal to the position of the voxel. Now you can apply an attribute to this point right after you have created the point using set point attrib, and the one you want to store as an attribute is this density value. So I'm gonna name this as density at pt, which is the point you have just created, with the value that you have retrieved from the volume as a density. Right. Now, if you go look back to the geometry spreadsheet, obviously you have a bunch of points being created other than the volume points. For the primitive, you have no extra ones, and so on. So currently, from the output of this node, you have both volumes and points. If you look at the informations, you have one volumes and extra several thousand points right here. Now, next thing I would like to do is to separate those volumes and points so that I can only pick up those points to see the exact values that I want to see. So I'm going to use split and split the geometry by using the group volume, which was declared right here. So from the first output you'll get the volume, and from the second output you'll get points that you have created using volume wrangle. Okay, and if you go back to the geometry spreadsheet for the point, you see that there's a additional density attribute, and each point have those different value, and this is exactly how you can retrieve the density value from the volume and be used to store it, and a point to use it for a debugging, for actually see what kind of values are stored in a density at each voxel. Okay, and right after this, maybe you can use this density value for any kind of purposes, something like using together with the color node with a ramp from attribute to look at the density attribute and color this based on the density value. Make this middle part close to yellow. Raise this up. Raise this up. Right. Like this. So this is one of the tricks you can use to convert a density value, or could also be used for velocity value, into a numerical values, convert it into as an attribute for a point. Then you'll be able to check it with the exact number, what exact number is stored in each voxel. This is sometimes pretty useful some case when you have some errors with the volume, when you are not getting the result you want. So this is the way you can check what kind of values are stored in each voxels. Right, so that's the last thing that I wanted to show you about the basics of volume together with the VEX. Now the one that I have shown you today is just the basics of volume, and there are a lot more you can do with this together with the VEX, and especially when it comes to do some create some simulations like fluid-like simulations or vector field based simulations. Using volume is pretty useful. So I'm gonna leave it as a different topic for later videos, but for today let's finish it with these basics. Now for the next episode, what I would like to talk about is a new feature from Houdini version 18.5, which is called dictionary. I'm going to show you what dictionary is, how you can use those dictionary with the VEX, and what it is useful for, what you can do with it, and what's the benefit of using it. Since this is the new feature, the dictionary is a new feature for VEX starting from 18.5 just being implemented, so there's not much information out there, but knowing how you can use dictionary will enable you to do a whole lot of complex stuff in an easy manner, which was not possible previously by just using arrays and so on. So please keep up, and this is it for today, and thank you for watching. If you like the video, please like it and subscribe, and see you next time. Thank you and goodbye.